Hello, I'd like to give you a quick demo of what you can actually do with my relay simulator. Here I'm building my 12-bit relay computer. So what I've done on the simulator is built every page on this is going to be one of the logic cards I'll build for my computer. So starting off, we'll start here with the sequencer. This is the heart of the machine. And as a demo, what I can do is I can interact with all these relays. So if I just hit reset here, you can see that the sequencer is now primed, and you saw that the relay contacts move, etc. on each relay. And now if I manually step the sequencer, you can see that the sequence pulses here are generated, and you can clearly see which wires, which lines should be live or not, and the state of the relays here. So it makes a very a good tool to develop relay-based logic, I think. So this is the sequencer. We also have on the relay computer, we have the controller card. This is where I write the microcode for all the instructions for the computer. I have some decoders here. These are 4 to 8 line decoders. One does the opcode, and then we have a source and a destination decoders as well. I have the standard registers A, B, C, and D. I have an I register for the instruction, a program counter. Program counter here is slightly different because it can be accessed by the address or data bus, and there's reasons for that I'll come to in another video. I have an incrementer to increment the address bus. I have 2 cards to implement the ALU logic for the computer. This card here is the first logic card, which does not C, NAND, NOR, and XNOR logic functions. ALU2 is similar, but this one does not B, or XOR, and AND. So with the combination of these 2 cards, I have all 7 logic gates, and I can also do not B or not C as for logic instructions. Here is a shift register card. Shift register can shift left or shift right, and it can also rotate left or right as well. So we've got a full capability of for shifting data in the ALU, and this will actually shift from B or C as well. You can choose which the 2 main registers you want to shift from. Here is the arithmetic ALU, and this card here will do addition, subtraction. Subtraction is 2's complement subtraction. It will also do increment and decrement. So I've got a function in here, it will either of the B or C register. So all those combinations this card can deal with for mathematical operations. And finally, I have a conditions register, which will load the conditions based on the output of the ALU. Up here I have a memory. So this is basically an implementation of a very simple static memory. And here I've written a program, and you can see the program. I've copied it out on here. This will load the A register immediately with a value of 85. It'll move the value of 85 from A to B. It will then load the A register with a value of 170, then move that to the C register, and then it will clear the A register. Then I've got 2 logic operations afterwards. The first one will be add, so it's going to add the B plus the C register. I'll put the result in the A register, and then I'm going to do a not C function. So let's take the value that's on the C register, which will be 170, not that, and then put the result in the D register. So there's the program. And then here I have the front page that actually controls the sim, and you can monitor what's going on. So I'm just going to stop the sim and restart it. There we go. And I'll bring the program back on here and we can see what's going on. So here we can see the sequencer, the abort lines. We can see the data bus in hex values, what's going on there. We can see the address bus in hex values, what's going on here. And here are the buttons that can control all the functions, and also they act as indicators to see what lines are currently being enabled. So first of all, I'll reset the sequencer as I did before, and then I'll start the clock. So what you can see here is the first instructions being loaded, and it's putting 5-5 onto the A register. And now the second instruction is moving that from A to B. The third instruction puts AA into the A register and moves that to C. There we go. Next instruction will clear the A register. Like so. The next instruction will add B plus C and put the result in A, which it has done. And then the final instruction here will do a not C. So whatever's on the C register, it will do not on that and put the result in D. And there it is, there's the program completed. I can stop the clock. So overall, you can see that the simulator will handle a lot of components, a lot of relays, all quite happily. This is simulator has been written in Python, and I'm by no means a great coder. So if anybody wants to come and help me with this project, who knows some Python and would like to improve this and add more functionality, please let me know. And if anybody's actually interested in the 12-bit relay computer that I'm building for real, again, please drop me a line.